All right, so this is a review for Robotics 2 final, second semester final. This will go all the way back. You can use your engineering notebook or any other papers you want. You cannot use the computer. Okay? So first thing I'm going to ask you is to remember the Six Sigma process. Remember the 5 steps of Six Sigma and be able to identify them. Okay, so if you have those 5, like I said, if you kept your notebook, if you didn't, they're pretty easy to find on the web. I also, if you go onto your computer later, I shared all those steps with you in the lessons, in the notes. What's the question?
I don't remember ever doing this on Sigma.
Six Sigma we did last.
I remember doing it on the computer, but I don't remember writing down notes.
Okay, if you go and look, I gave you paper notes to it. There's also notes in classroom when you go back to those. In following the Six Sigma goals there, what do we need before we start data on a goal? So if we're coming up with a project, what do we need first? What kind of data do we first need to come up with? Hypotheses, that works. It's not necessarily so much for Six Sigma. Six Sigma, you're creating a project, so it's not a hypothesis. You know where you're going.
Start off with like the blueprints and the.
What kind of data do? So you gather data, right? That's one of the stage. What kind of data do you need first? In the end, you're going to find out data at the end. You need baseline data at the beginning, right? So you have to have some data that starts you up. So far, so good. What makes a good Six Sigma project? Actually, let's go back to question 1 because he's still looking it up. But stay with me. What are the 5 steps in the Six Sigma process? Do you remember? You have your notes out, so what are the 5 steps?
It's define, measure, analyze, improve, and control.
Define, measure, analyze, improve, and control. You finding them now?
I do not have that.
Well, she has it over there if you talk to her nicely.
It's all the way back. I remember us putting these in there. It's like the first thing you put in there.
You find it, Cordell?
I don't have that.
Okay. It's in classroom, or if you're coming to me during lunch, I can help you out. Okay. What makes a good project? What makes a good project in Six Sigma? Is a project, okay, stop searching. Listen, I don't have to have time for search every question. We'll never get through the review. So Six Sigma projects, do you want a project that takes a year for completion? Why not?
Because that's too long.
Too long. So the project has to have a short-term definite goal, right?
Yeah, 6 months.
4 to 6 months. See, very good. What kind of objective do you want? Do you want one of those objectives like improve company morale? What kind of objective do we call improving company morale? Can you really measure that?
No.
No, it's fuzzy, right? There's no way to do it. It's a terrible goal. So what kind of project do you want? One that's short, 4 to 6 months. One that's linked to the actual business priorities. Does that make sense? Something that's actually going to be monetarily effective for the business, right? Does that make sense? Talk about project management. So project management, what are the points to it? When you're managing the project itself, what do you want to make sure you do? When you're managing the project, what do you want to make sure you do? Do you want to review it? Okay. Do you want to make sure that you sustain the gains? That means any good stuff you got keeps going, right? Do you care about monetary success? Is that really your focus? Your project? No. That falls under sustain the gains. It's outside of you. Location and space. We're leaving Six Sigma. That's it. Location and space. When you're defining an object's location in space, if we've got a ball and it's sitting here, how many degrees of freedom must be defined to find its location in space? Ashton, you should be able to answer this one. What's the optimum degrees of freedom? We talked about 3 is the minimum, right? What's the optimum?
6.
6. 6 is always the optimum for degrees of freedom. So when we refer to a degree of freedom, what are we talking about?
The way you can move.
Hmm?
The way it can move.
What do you mean?
If it can move this way.
Okay, use your hand. When I define the degrees of freedom in my hand, there's about 24. Actually, I think it's 26. What am I defining? The joints, right? Very good. What's an end effector? A claw. What else? Give me a couple other end effectors. A hook. A laser. Could you have just a poker? Be a boring end effector, but you could have just a poker, a welder. All these things are end effectors, right? Going too fast, Mackenzie? Okay. So counting degrees of freedom, what's the focus on? If you're counting degrees of freedom, does the end effector count?
No.
Cordell, does the end effector count?
No.
Okay, what are you counting when you count degrees of freedom?
Like how many?
Like my hands. What am I counting?
What parts move?
What do we call those?
Joints.
Joints. Very good. Okay, here's a good one for you. I already told you there's 26 degrees of freedom in my hand, right? How many degrees of freedom in the human body do you think? How many?
Your neck has a lot. Your hands have a lot. Your legs got a lot.
254. Your body's incredible. 254 degrees of freedom. That's right. Some moron. I thought about making that an assignment, but you can find that answer on the web too easy. It would be an evil assignment to make people label all possible, find all 254. Because your neck can go up and down, around, side to side, back, front. It's credible. You're right. Your neck has a ton. Just in your hands are stupid with them. Your toes and your feet. Your feet have a bunch. If you've never thought about it, you can actually move parts of your feet that aren't your toes. Have you ever thought about that? Wiggle now and feel them. You can actually feel like right across the top of the arc, or right across the top. You can actually feel that move. there's actually a joint there. Doesn't go very far, but it's still a joint, and therefore a degree of freedom. Okay. Why should you keep an engineering notebook?
So you can look back in case there's a problem.
Okay, is it just problems?
You can also see how you change the project.
Okay, you can see how the project changed. Can you see how the project originated? So if you invented a claw right there, and you have an engineering notebook that tracks it, can you use that for patent information? So if suddenly somebody comes out with the same claw and makes some money, can you sue them based on your engineering notebook? Yeah. Legally, it gives you a way to track back to the original thought and see that it was yours on a specific date that it wasn't theirs. Okay. So engineering notebooks, what are some of the best practices? Best practice means what are the things you should do with your engineering notebook?
Graph.
So quad ruled paper, that's what they call that, quad, right? That's best because it allows you to draw diagrams. What else? On your engineering notebook, what else have been the important things I've checked for every time?
Dates.
Dates,
Signature.
page numbers,
Diagram.
If you
diagrams,
your signature.
signature. How about pen or pencil? Pen. Oh, why always pen?
Because it's permanent and can't be erased.
Yeah, legally they can't make those changes. Your buddy can't come and erase all your entries randomly and take credit for your work. Should you leave a lot of blank spaces?
No, but if you do, make sure you cross it out.
Good. Okay, that's the you've kind of seen. I'm hitting all the parts of our TEKS in one test, and some of this would have been nice if we'd had a first semester final, but that's fine because it's good for you guys to remember. I think, and before I go on, each question is worth 4 points, and there are 30 questions for those of you who do math. 25 times 4 gets you 100, so there's 5 more questions than you possibly need in here. So you can miss quite a few because we go over a lot of stuff, and I don't expect you to be expert at everything, but I expect you to get it pretty good. So we'll talk about gears and gear trains, and you need to know the definitions of the different things, and that comes right out of that notebook page that I printed for you. Right? Do you have those pages? You should check. We did all the gear stuff, and I printed those pages for you. So you'll need to be able to define what the gears are. Did you not keep them?
No, I did.
Okay.
They're in here.
So you'll need to define definitions. You'll need to identify the different types of gears. Do you remember all the different types of gears? Yeah, all that. It's all in there. So defining the types of gears, defining the difference between like a gear and a sprocket and a rotational speed and whatever else. This is probably the largest section on it because it was really the one we did. It was really what we spent the last bit of this semester doing, was working on gears and gearing.
Yeah, I don't have that.
Yeah, you'll have to go back and find it, or come talk to me sometime, or it's available in classroom. You can print it off. Okay. Know how to get a gear ratio. How is gear ratio? What is important to know about gear ratio? What's the equation?
It's
The equation is driven over
driver.
driven over driver. So driven is the thing that power's applied to, or the first gear. Driven over driver, right? Did you write that down? I love that huff. How do you tell the difference between torque and speed?
If I forget which side it is. If it's higher on one side.
Okay, which side?
It's on the left side.
So if the driven is smaller,
If it's bigger,
if the driven is bigger, what do you get?
then you're getting more torque. It's bigger. Right. No, if you're getting more speed, if it's bigger, and
No, you were right. Think about this. You were right.
the driven one has to be bigger.
So if this is the driver, and this is the driven, and this has 25 teeth and this has 50 teeth, what's going to be the end result? Which one is going to go? Is the driver faster or slower than the driven?
It's spinning faster than the.
So I'm losing speed, but I'm gaining torque. So small to large is torque. Oops, can't spell torque. Yeah, torque. What's large to small?
Speed.
So large to small is speed. Stay over there. Rude thing. That makes sense now? And we know that when we tried it, you could keep going real fast, but the minute you applied weight to it, there wasn't any power behind it. Match gear names, definitions. What do we call a gear train with a shaft that has multiple gears attached to it? What's a gear train with the shaft with multiple gears attached to it called? What kind of gear train is it?
It's called a compound gear.
It's called the compound gear train. When you're doing gear ratios and you have multiple gears, how do you get the final gear ratio? If I've got multiple gears, let's say I got 3 gears. I've got one with 10 teeth. Then the one next to it has 25 teeth. And the last one has 30 teeth. And the 30 teeth is the driver. So 30 is the driver. And then everything runs. How would I find the gear ratio for this train? Mackenzie, how would I find the gear ratio for this train?
You do 10 and 25 first. And
Now think about it. Which is the driver? Which is the one that has the power put to it?
you do the 30 to 25 first.
Pay attention to which is the driver. Which one of those is getting input to power, right? Right? Okay, so what would I do?
They're both divisible by 5.
Well, don't go there.
Um,
How would I figure? Which one of these is driven?
the 25 is driven.
So it goes driven over driver, right? 25 over.
30.
And now what do I do from there?
You simplify it.
No, not yet.
Then
Then I move to the next one, right? At this point, what is the 25? Is it the driven or the driver?
it's the driver.
Driver now. So So I've got the driver's 25, driven is 10. How do I write that?
You do 10 over 25.
So I multiply them, right? Now I simplify. So it has 25 both top and bottom of the equation. The first one is 25 over 30 times 10 over 25. The two 25s cancel out to 1 each, right? How about the 10 and 30? How about the 10 and 30?
They're both divisible by 10.
So this is 3 and this is 1. So what do I get at the end? A 1 to 3, right? That make sense? That's my end ratio, is 1 to 3. Driven to driver. Any questions? All right, so that's the final. Now I'm going to stop the thing over here. Use these couple of minutes to drag all the stuff, all your notes out, and put them together so you'll have them for tomorrow.